In the last class, we saw that mixer can be implemented using a device which has second order of nonlinearity. Now we are going to see that how a switch can be used for mixing. So whenever we want to do mixing, we basically want to do multiplication. So if we have any device which is able to ultimately multiply two sinusoids, then it can be used for mixing purpose or as a mixer. So when we are claiming that switch can also be used as mixer, that means we are basically saying that switch can also be used for multiplying two sinusoids. Now let us see that how a switch can multiply two sinusoids, RF and LO. So let us first consider an ideal switch here. So the first end, of course, is fed with RF signal. The switch is controlled by LO signal, and the output is taken here. And this is VIF. So actually by IF we mean up converted or down converted, but we will see that on the output side here, even for the nonlinearity case, there were so many frequency components, only two of them were of usefulness. So only out of infinitely many output components, only two were either up converted or down converted. In fact, when we will be using only one of them, not both. So now let us see that how output will contain product of LO and RF. So here we will assume that switch is on, that means closed for LO greater than 0, and off, that means open for VLO less than 0. So switch is ideal. It suddenly switches from close to open state as LO changes from one sign to another sign. Now VLO we have been taking this form, and VRF as this one. So objective is to find VO, and from there, and then find IF. So there are certain steps that we will follow, and these steps are going to be very general. We will be following this for subsequent mixers analysis. So I will point out the steps. So first is for one half of LO, find out the output. Say for the first half. So let us assume that VLO is greater than 0. And for this case, we want to know what will be output. So based upon our assumption, since LO is greater than 0, so switch is going to be on. That means closed. And in this case, we will draw the signal circuit, modified circuit. So this implies on switch. So from here we can see that output is equal to RF. Now we consider the second half of LO. So let us say that now it is going to be less than 0. So this implies off switch. So now we draw the equivalent circuit. So here we see that RF gets isolated from the output, and output is actually 0. So now we know the output for both the half of LO, and this will now repeat. So in step 3, what we do is we combine the two halves to write output for complete cycle. So we saw that output was RF for LO greater than 0, and it was 0 for LO less than 0. That means second half. So here we can write both the half in terms of RF. So first half can be written 1 into VRF, second half can be written as 0 into VRF. Since RF is common, so one can take RF outside, and what we will be left is 1 VLO greater than 0, 0 for VLO less than 0. Now here what we see is this is basically, and this will repeat every cycle. So what we see is this is nothing but a square wave. So this is for one cycle, and cycle will repeat. So the final output is basically equivalent to VRF into square wave. Say like this. here. So I am showing here graphically what we have been writing up till now mathematically. Between 0 and 1. And we know that this square wave is in terms of Fourier component, this mathematical expression. Here. And this RF we have been taking sinusoidal signal like this. So this RF is this one, and this square wave is this infinite components. So here, what is happening is basically this RF is getting multiplied with square wave, and it will get multiplied with the various components of the square wave, and one of the components is LO. So what we will get as VIF now is A cos omega RFT into 2 by pi cos omega LO T. So when expanded, this will become A by pi cos omega RF minus omega LO T plus cos omega RF plus omega LO T. So we see that mixer using this switch is getting multiplied because RF is getting multiplied with the LO component present in the square wave, which results because of the LO. So this is mathematically, and in frequency domain, we can see that what is happening here is so in frequency domain, this RF signal basically gets convolved with square wave. So we can see this using spectral components also. For example, this is omega RF. This when gets convolved with square wave, basically gets convolved with this train of pulses. One is a DC, and then others are at various frequency component. For example, at omega LO, at minus omega LO, and then at minus 3 omega LO, and at plus 3 omega LO, so on and so forth. So here we see that what we are actually interested in, that means VIF is convolution of this RF with this LO and with this minus LO. So this is what we get as the up converted and down converted signal. Now we would like to see So what is the linearity of this mixer, switch-based mixer? Because it will always be taking input as a band of frequencies. So it should be able to do this translation for each of those frequency component. Not only that, when the receiver moves closer to the transmitter or moves away from the transmitter, the amplitude of the received signal varies. So this translation of the incoming signal should not get affected by the amplitude of the incoming signal. So that is why the linearity of mixer is important. Now let us see that what will be the linearity of this switch-based mixer. So here we have our mixer, which is having input X and output Y. So for this to be linear, there are three properties which should get satisfied. First is if input is 0, then of course output should also be 0. Second is if X1 input implies Y1 output, which we'll call as f of X1, then scaling this input should imply a scaled up version of output. And third is that if X1 implies Y1 and X2 implies Y2, then linear combination of these two inputs should imply a linear combination of their corresponding output. So if these three conditions are being satisfied by this mixer, then we can say that this is linear. And here we know that there is another control input, VLO, second input. So there are two inputs. One is RF, other is LO. So we can test linearity of this with respect to each of these two ports. So first, let us test the linearity. With respect to RF port. This is the most important port. So for this case, what we will do, we will keep only the RF port outside. LO port we will keep inside the block. So this is the scenario. And now we will assume that we have a box like this, where only these two RF and VO ports are visible. So now let us see what happens when VRF is equal to 0. So when VRF is 0, uh, output is obviously going to be 0 for all the time, because output was anyway 0 for uh, VLO low. That time switch used to open and output used to be equal to 0. But when switch was closed, that time it was equal to input, which is RF. So here RF is 0, so output is going to be 0. Now, for the case when we have output equal to VRF into square wave, suppose this is the case. And now what we want to do is scale up the RF. So RF here is A cos omega RFT square wave. Now suppose we scale up this RF, and we now take K into A cos omega RFT. So we now have new output. So this output here you can see is K into the previous output. So when we scaled up the input, output also got scaled up. So the second property is also valid here. Now we want to say what happens with the third requirement. So in this case, we are going to take input, which is going to be linear combination of two different inputs, RF1T and K2 into A cos omega RF2T. So in this case, also the output is going to be input multiplied by square wave. That means K1 into A cos omega RF1T plus K2 A cos omega RF2T into square wave. So now these two inputs can individually be multiplied with the square wave. So this clearly says that now the new this new output is K1 into VO1 plus K2 into VO2. So VO1 is this one, which we would have got for this input. VO2 is this output, which you would have got for this input. So here we see that linearity is valid. So this implies that switch mixer is linear with respect to RF, that is input mode. Now we'd like to see that what is the linearity behavior of this mixer with respect to the LO port. So now we will have to take the RF port inside the box, and LO will now be outside, so that we continue to see only two ports. So we again have a two port block. So here also, if LO is equal to 0, switch is going to be off. So this implies VO is going to be 0. So in this case, the first property is valid. No input, no output. But the problem comes when we move for the second case. So for the second case, what we will have to do, we have to take VLO. Now we have been taking VLO as B cos omega LO T, right? And in this case, we have been getting output as VRF multiplied by a square wave. So this is the output with the simple input LO. Now we take so we take scaled up LO, and in this case our VLO we will be calling as VLO1. This becomes K into B cos omega LO T. So we have scaled up the amplitude. Now in this case also we know that if VLO1 is greater than 0, this implies on switch, and this implies output is new output rather is again going to be VRF only. And when VLO1 is 0 or maybe negative, this implies off switch, and VO1 new output is going to be 0, equal to 0 into VRF. So we see that the complete output actually remains what it was earlier without scaled up LO. So this scaling up LO has not led to any change in the output. So we can see that this is again VRF into a square wave. So what we find is that in this case, output is not scaled. So that is why it is non-linear with respect to LO port. Now regarding the third property, we can see that there also scaling up is involved. So when the two inputs they are scaled, output should also get scaled up. Since scaling is not valid with respect to the LO port, so even the third property also will not get satisfied. However, the sum part of the third property, that means the sum of two inputs leading to sum of two outputs, that part will be valid, because here this multiplication, this is linear. So if this RF is sum of two, so this can be distributed over two individual sums leading to two different sums. But scaling, because scaling is not valid, so third property will not be valid. So that is why the linearity of this mixer, switch-based mixer with respect to LO is not true. So we saw that switch can be used for mixing purpose, and fortunately with respect to RF port it is linear also. So here now then question comes that which of the two types of devices, non-linearity based device or mixer based device, can be uh, should be preferred for mixer implementation. So one of the ways in which we can see the advantage of one over another is a parameter called Spurs. And these are the unwanted frequency components. The output. So we saw that both the switch-based and non-linearity-based, they will create a very large number of unwanted frequency components. But here you can see that for switch-based mixer, so for the switch case, output is RF multiplied by square wave, which was 1 by 2 plus 2 by pi cos omega LOT minus 1 by 3, all the odd harmonics. So here there will be infinite many frequency components. First is going to be omega RF arising because of this DC term. Then omega RF plus minus omega LO. Then omega RF plus minus 3 omega LO, and so on and so forth. Omega RF plus minus in general 2m minus 1 omega LO, where m is equal to 1, 2, 3, so on and so forth. But if you see the spurs of nonlinear based mixer, for example, diode based, so these are infinite, of course. So suppose output is given by this. Here. So we have seen that this nth term itself is going to give rise to these many frequency components. Here. So here also we will have infinitely many components, but total number of components here are going to be a lot more than the previous case. So in this case, filtering has to be stronger compared with the previous one. And here we can see that this is the desired one, and the closest one that is going to appear is this one, omega RF, and then this one. So even this one is going to be 2 LO times separated from the desired one, right? So here there is a wide gap between the frequency components, and filtering out this desired one is going to be easier compared with this case, nonlinearity based case, where the frequency components, they are all going to be very close to each other. So that is why switch-based mixers are more preferred compared with the nonlinearity. And so in future classes, when we study mixers, we will be studying switch-based mixers. Now to start the study of these mixers, we will start with the simplest mixer and then try to find out the conversion gain and leakages. So the first mixer that we are going to study is unbalanced. As the name suggests, that means ports are going to be single-ended and passive. That means output amplitude is going to be less than input. And we are going to use MOS. And this is actually switch-based mixer. So here MOS is going to play the role of switch. So whatever architecture we just now saw, in there we are going to implement the switch using a MOS. So we take MOS, we feed LO to the gate, and we connect RF to source, and drain to output. So we know that in this case, MOS is going to act as a switch if LO amplitude is sufficiently large. So ideally, VLO should be taken a square wave. Or very large amplitude sinusoid can also be used for this purpose. So now we will try to find out the conversion gain. So let us take VLO, a square wave. But as I pointed out, it need not be a square wave. It can be cosine, but with large amplitude, so that it switches the MOS quickly. So here amplitude need not be 1. In fact, it should be significantly greater than 1. So for this duration, it is going to be on. And for this duration, this is going to be off. So on and so forth. So this is how MOS will behave. So we have seen that when MOS closes, in that case, LO is going to be equal to RF. And when it is MOS is off, in that case, LO, sorry, this we have written wrong here. This is output, or rather VIF. So when MOS is off, output is going to be 0. When MOS is closed, output is going to be equal to RF. So this is what is going to happen, and this again can be written in this form. So here we are saying LO less than 0, but we have taken signal which is between 0 and certain positive. So we can say that this is case for VLO is equal to 0. So we are going to get square wave, but this square wave will always be between 0 and 1. So here we could have started with LO like this, between a positive and negative value. This LO is also possible. But whether you take this LO of type 1 or type 2, in both the cases, what you will get here is this square wave between 0 and 1. So again, we are going to get same thing, that is 1 by 2 plus 2 by pi cos omega LO t minus 1 by 3 cos 3 omega LOT and so on and so forth. So the VIF part is going to be this RF multiplied with this, and the RF is cos RFT multiplied by 2 by pi cos omega LO t. So here we see that the amplitude output is A by pi, and the amplitude of input was A. So therefore the conversion gain GC is A by pi by A, that means 1 by pi, and this is less than 1, that is why this is passive. So this is passive mixer. Now this can be taken more realistic in a sense that we can assume certain internal resistance for RF and then try to find what will be the output. So here now we have included RS also, and we want to see that how this will affect the output or the conversion gain. So we consider two cases when switch was closed. It was for this case. So in this case, the equivalent circuit is going to be like this. So this is a MOS. Here we have RF. This is RS, and the load is here. So now we can see that output is no longer equal to RF, rather it is fraction of it because of the source resistance. Now for the second case, when VLO is 0, or if you want to take negative VLO, in this case MOS is going to be open circuited. So here we see that output remains same because it is 0. So now we can combine two halves. Now here, in fact, this factor should also be taken out. So we again have the same square wave which we had been getting. There's no change in it. So only change is this factor which has appeared. So if you say VIF, it is going to be so from here what we will get is 2 by pi cos omega LO t. So when you expand this, so what we will get is RL plus RS into A by pi So this is the amplitude of the output, and input amplitude is A. So therefore conversion gain is RL divided by RL plus RS into 1 by pi. So compared with the previous case, this is the additional factor that has appeared, and this is only going to reduce the conversion gain. Right. Now regarding feed through, so here we did not consider any parasitic capacitors. So we have simply substituted MOS by perfectly open switch or by closed switch. So we did not consider any parasitic. No parasitics were considered. But even in absence of them, we find that there is one feed through that is from RF to IF. So we have this mixer. So here we found that output was VRF into square wave. like this. So desired components were, of course, product of these two. But here we see that there is one more component present, and that is because of product of RF and this DC, which is present in the square wave. So that leads to 1/2 VRF at the output. So we see that RF is able to reach to the output because of this DC present in the square wave. So we say that RF to IF feed through exist because of the DC in the square wave. So this DC has nothing to do with the DC in the LO, but this is DC of the switching phenomena. LO arising because of the this is square wave arising because of the on and off state of the switch. So we will see that then what to do so that these kinds of feed through or leakage can be avoided.